and today's video is on calorimetry.
So, calorimetry is heat measurement. This allows us to see the energy consequences of a chemical reaction. Is it exothermic and releasing energy to the environment, or endothermic and absorbing energy from the environment? Also, to what extent or to what degree is it? The total internal energy of a chemical system at constant pressure we call enthalpy. It's an important idea and a big word for us in this course. Of course, we can't measure enthalpy directly. How could we know the total internal energy of a system? So what we do is we watch and measure the heat flow into and out of the system, and that way we can get a handle on the changes of the enthalpy that take place due to a chemical reaction. So notice that the enthalpy we denote as a capital H, and the enthalpy change we call delta H. Remember the thermal energy and heat? You recall Q equal mc delta T. There's the heat flow into or out of an object. That's in joules. M is the mass of the object. That'll be in grams. C, the thermal heat capacity of the object, or the specific heat capacity of the object, I guess we should call it. And this is joule per gram degree Celsius. Delta T, of course, is the change in temperature of the object. We'll measure that one in degrees Celsius. So we use this for chemical reactions by setting up a certain kind of situation. It's an insulated environment. So here we have such a situation. It's a schematic view. We'll have the reaction in the inside here. We'll have some surroundings in the reaction, probably water in our case. And then we'll have some insulation around the outside of the reaction to prevent heat from entering or leaving the system from the outside world. Okay, in this way, whatever heat is generated by the reaction will be absorbed by the surroundings, and any heat gained by the reaction will be lost by the surroundings. Hopefully, no heat will flow into or out of this system from outside. In an equation, you could say that the heat flow into the reaction is the heat flow out of the surroundings. Notice the negative sign. So by using a set of surroundings we can easily quantify, we can get the heat flow into or out of the reaction. Let's have a look. Here we have the heat flow out of the reaction equal to negative mc delta T from the surroundings. So for instance, we could make a calorimeter to measure the heat of reaction that enters or leaves an aqueous solution. Maybe this one. Let's take hydrochloric acid and sodium hydroxide. They'll neutralize those two and get water and sodium chloride. Let's try to determine how much heat energy is evolved or absorbed due to this reaction. And we'll do that when 1 mole of this reaction takes place. In other words, when 1 mole of hydrochloric acid and 1 mole of sodium hydroxide, etc. react. This will tell us the amount of internal energy that the system gained or lost, i.e. delta H. So here's a sample setup. This is the famous coffee cup calorimeter. What you need is 1 or maybe 2 nested foam coffee cups with a lid on top, and we'll use a known volume and mass of solution inside. Measure this with a thermometer. We'll use a LabQuest digital data acquisition unit, but even a regular thermometer will do. The idea is to measure the temperature as time passes along and the reaction progresses. We expect this reaction to be exothermic. Can you see the temperature rising on the screen of the LabQuest? That rising temperature is delta T. So the reaction will be inside and will give off or gain heat from the known mass of water that will be the surroundings. Think of it this way. The reaction is between the solute particles and the water is the surroundings. So, how's it actually done? What's the technique? First, stabilize the temperature of the reactant solutions. If you can get them to room temperature, that's best. Second, measure the temperature of the solutions. In other words, start data collection before you mix them together. Then pour together the two known volumes at known concentrations, and remember the temperature is known too, and we have to arrange this so that one reactant will be used completely. So keep one reactant slightly in excess to ensure that the reaction that you're interested in is completely reacted. So for example, 25 mL of 1 molar HCl, you might use 35 mL of 1 molar sodium hydroxide to ensure that the hydrogen chloride, all the hydrochloric acid, was totally reacted. Be sure that you cover the system with an insulated lid and stir gently while monitoring the temperature. You should get a relationship with temperature and time looks something like this. Certainly in our reaction, we expect this reaction to be exothermic and get a positive delta T. Notice the temperature falls down here. What's going on? Hopefully the effect will be small because the system will be losing some heat to the outside world. Remember, insulation isn't perfect. Finally, analyze the data this way. Delta H for the reaction will be the heat flow that flowed into or out of the surroundings. And if you get that on a mole basis, you can get it by dividing by the number of moles of reactants that were consumed. In our case, we'll have negative MC delta T for the water, divided by the number of moles of reactant consumed. In our case, hydrogen chloride or hydrochloric acid. So that's the basics of calorimetry, at least our quick introduction. And we are doing this first because it really gives us an early view of that big idea we have, enthalpy changes. They're really important in this unit we're starting on chemical kinetics. So here's your assignment. First, have a look at my website and get the Coffee Cup Calorimetry Lab handout. Make sure you do a flowchart. Second, see the next couple videos in this Chem 12 playlist for a little bit more explanation on this topic of calorimetry. That's it. Thank you, and see you soon. Have a look at the next video in this playlist for more on the topic, and stay tuned for our next lesson, lesson number 2, Hess's Law.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!